Okay. So first of all, like this worksheet is just asking you to balance the equation and predict and say what kind of reaction it is. So it's just identification of reaction type, which that's kind of the first step in being able to predict products, is being able to determine what kind of reaction is going to happen. So up here, we can see that we have two smaller things becoming a bigger molecule. So what kind of reaction would that be?
Synthesis.
Yeah, it would be synthesis. I actually don't see it on the list here, but we will just add it. Synthesis. Okay. And then if we want to balance this equation, we can see that we have 4 oxygens on the reactant side, and we have 3 oxygens on our product side. So we need to fix that, and it's going to be really hard to fix that with an odd number of oxygens on this product side. So what I want to do is I want to make that number of oxygens an even number. So what can we put as a coefficient here to make this an even number of oxygens? I don't know if y'all can see it. I'll move it a little closer.
2.
Yeah, we can put a 2. So now we have 6 oxygens over here, and we have 2 here and 2 here. Which coefficient where do we want to put our coefficient? Do we want to put it in front of the SO2 or in front of the O2?
I think that we should put it in front of the SO2 because since you put the 2 in front of the SO3 in the product side, you're going to need a second S as well.
Perfect. Okay, so we noticed. So I think it was Camden. I don't actually know, but we noticed that by putting this 2 on the product side, we made it to where there's 2 sulfurs. So we also need to make 2 sulfurs on the reactant side. So we're going to put that 2 over here, and that makes it to where we have 4 oxygens in this first compound and 2 in the second to get to a total of 6. But if we put the 2 on the O2, then we'd still be short sulfurs even though we fixed our oxygen problem. So we want to do the least number of steps to balance our equation. So now we have 2 SO2, O2, and 2 SO3. And remember, we always have to fill in that 1 on Schoology. If you're responding to an answer either on Khan Academy or on Schoology, you have to fill in the 1. Okay? Alright, so that's the first one. Let's look at the second one. We're not worried about this. Let's see. Okay, so looking at this reaction, what kind of reaction do we have here? We have a lone element and a compound. So what kind of reaction do we have here?
Is that a single replacement?
Perfect! It's a single replacement. So we have a lone element, aluminum's out by itself, and then we have a single ionic compound. So aluminum is going to come in or replace something in our ionic compound. And so just looking at these reactants here, what is aluminum going to replace? Yeah, it's going to replace manganese because aluminum is a cation. And cations can only replace other cations. So aluminum, as a cation, is going to replace the cation in our compound. It's going to replace manganese, kick manganese out. So manganese is out by itself now. And then we redid our crisscross over here. Aluminum has a +3 charge. Oxygen has a -2 charge. So when you cross down, you get Al2O3. Okay? So even though the product's already listed for us, it's kind of a good practice to make sure that we can also predict the products, because that's the biggest part of this particular zone on your matrix. Okay, so now we know this is going to be single replacement, and it wants us to balance. So there's a couple things out of balance here. What's one thing that's out of balance? Move it closer again. Anybody? So I see aluminum. There's 2 aluminums on the product side and only 1 on the reactant side. And then also oxygen. We have 2 oxygens on our reactants and 3 in the product side. So for me, the thing that I immediately think is I have an odd number of oxygens in my product side, and I'm never going to be able to correct for the number of oxygens with a whole number. I'd have to put 1.5 over here to correct for the number of oxygens. And we can't do that because our coefficients have to be a whole number. So I know that the first thing I'm going to do here is I'm going to make an even number of oxygens by putting a 2 in front of Al2O3. So now I have 6 oxygens, and I can put a number in front of this over here. I can put 3 to make 6 oxygens on the reactant side. And then from there, I messed up manganese. I have 3 manganese over on my reactant side now, so I need to put a 3 in front of the manganese on the product side. And then I need to balance aluminum. I have 2 times 2, so I have 4 aluminums on the product side. So I'm going to put a 4 in front of aluminum on the reactant side. Questions on that? Does that make sense to everybody? Alright. If we're good, then I'll just keep going. Alright. Let's look at some where we have to actually write the reactants and products. Okay, so it says phosphoric acid and calcium hydroxide react to produce some other stuff. So, the first thing we need to start with here is doing our crisscrosses. We need to crisscross correctly to figure out what our reactants are and what our products are before we do any balancing. So phosphoric acid, we know an acid is going to have hydrogen as the first part, but what's our second part going to be for phosphoric acid? Hi, Swami.
Hi, Miss Gregory.
We were talking about phosphoric acid. Swami's like walking or in the car or something. Okay, so phosphoric acid. So is this going to be an element or a polyatomic ion?
It's going to be a polyatomic.
Okay, and what polyatomic ion is it going to be? Phosphate, which is PO4 with a 3 minus charge. And we know hydrogen's a +1. So what do we get when we crisscross? H3PO4. Perfect. Okay. Then we have calcium hydroxide. So I have my calcium ion and my OH with a -1 charge. Calcium has a +2 charge. So when we crisscross, we get Ca1, but we don't show that 1. And then we're going to end up with 2 hydroxides. So I'm going to open my parentheses, OH, close parentheses, and then put that 2 outside of the parentheses. Okay. Okay, then we have calcium phosphate as one of our products. We're going to have calcium, still with a +2 charge, but this time it's bonded to our PO4 3 minus. So when we crisscross, we're going to get Ca3. Then we're going to end up with 2 phosphates. So I'm going to do PO4, close parentheses, and then put my 2 outside the parentheses. Okay, and then we have water, which we know is H2O, dihydrogen monoxide. But when you are balancing equations that have a hydroxide ion in them, it's easier to balance if you write water as its component ions. What I mean by that is that water is made up of a hydrogen ion and a hydroxide ion. So we can write it as HOH, which shows that there's 1 hydrogen and 1 hydroxide. So then when we're trying to balance, we can look at hydroxide as one thing and balance this hydroxide on the reactants with the hydroxide on the product side. And we can balance the hydrogen in the water with the hydrogens in the acid. Does anybody have questions about that? Need to say it again? Okay. Okay, so now we just have to balance. So what's something that's out of balance? Calcium, okay, perfect. So we have 3 calciums on our product side, and we only have 1 on our reactant side. So to fix that, we can put a 3 in front of calcium hydroxide. Okay, what else is out of balance? Okay, so you're actually right. The oxygen is out of balance. But when we're balancing equations, it's usually easier to think of our polyatomic ions as one thing. So the oxygen here is part of the hydroxide ion, and the oxygen here is part of the phosphate ion. So instead of balancing and trying to add up all of the oxygens, we can look at the number of phosphates on each side and the number of hydroxides on each side. So what I look at here, I don't look and try and count up the oxygens. I look and I say, okay, there's 2 phosphates on my product side and only 1 on my reactant side. And there's 2 hydroxides on my reactant side and only 1 on my product side. Does that make sense?
Yeah.
So it makes it a little easier to balance. So let's do hydroxide first. So how could we fix the number of hydroxides? Oh, actually, I said it wrong. There's actually 6 hydroxides because we put this coefficient of a 3. So how can we fix and make the correct number of hydroxides on our product side?
Put a 6 in front of a hydroxide on the product.
Well, we don't just have hydroxide. What is this molecule over here? The HOH.
Oh, wait, that's technically water.
That's water, but you're still right. We can put a 6 in front of water, so now there's 6 hydrogens and 6 hydroxides. This is kind of actually a challenging one to balance. So 6 hydrogens and 6 hydroxides. Okay, so we fixed our hydroxide. We have 6 hydroxides, 6 hydroxides. But when we put that 6 here, we made there be 6 hydrogens, and we only have 3 hydrogens over here on the reactant side. So how could we fix that?
We put a 2 in front of the hydrogen and on the reactant side.
Well,
That
yes.
also solves the issue with phosphate.
Perfect.
On both sides.
Perfect. Yeah. So we put a 2 in front of the phosphoric acid on our reactant side, which makes there be 6 hydrogens, but also makes it to where we have 2 phosphates. We have 1 phosphate in each of our phosphoric acid molecules. And we had 2 phosphates on our product side, so it actually fixed both things at once. So now we can go back and check. We have 2 times 3, 6 hydrogens on the reactant side. We have 6 hydrogens on the product side. We have 2 phosphates on the reactant side and 2 phosphates on the product side. And then we have 3 calciums on the reactants, 3 calciums on the products, and 2 times 3, 6 hydroxides in the reactants, and 6 hydroxide in the product side. So now we have a balanced chemical equation. So now that we went through all that headache of balancing, what kind of reaction is this?
Is that a double reaction?
Yes, it is double replacement. So if you look carefully at it, you might notice that hydrogen came over and bonded with OH, so we got HOH, and then calcium bonded with the phosphate, calcium phosphate. So they switched partners, the cation swapped places, and we got our opposite products. So it is a double replacement reaction. Let's see, I'm trying to find one that's not a double replacement reaction. Let's see. Let's look at number 11 right here. Okay, let's see. So number 11, we have Mg plus O2. What kind of reaction is that going to be?
That would probably be a, what is it? Synthesis? Yeah, synthesis.
Synthesis, perfect. So we have 2 elements by themselves. Even though oxygen is diatomic, so it comes in a pair, it's still by itself. It doesn't have any other type of atom with it. So when we have 2 individual elements like by themselves, that's how you know it's going to be a synthesis reaction. So we're just going to have these 2 things coming together to form, in this case, it's going to form an ionic compound because we have a metal coming together with a non-metal. So if we're going to have an ionic compound forming, what do we have to do to figure out the formula for our ionic compound? What's that method? It involves like this kind of thing going on. Yeah, okay, so we got to do our crisscross to figure out what our product's going to look like. So we have magnesium, it's going to be bonding with oxygen. And it's important to note that we don't carry the subscript over because oxygen now has a buddy that's not itself. So it doesn't need to be paired up anymore. We don't carry any subscripts over. We're going to re-crisscross. So magnesium has a +2 charge and oxygen has a -2 charge. So when we crisscross, what are we going to get? Actually, we'll do it over here first. +2, O -2. We get Mg2O2. But what do we know we have to do with this? Can we leave it as Mg2O2? Yeah, we have to simplify it because it's ionic. To simplify, it's just down to MgO. So that's our product of our reaction. Is this a balanced chemical equation? Mg plus O2 gives us MgO. It's not balanced. So we have 2 oxygens in our reactant side and only 1 oxygen on our product side. So to fix that, we got to put a 2 in front of magnesium oxide. And then now we threw off our magnesium because now we have 2 magnesiums on the products and only 1 on the reactants. So we have to put a 2 in front of magnesium on the reactant side as well. All right. Any questions on that one? Everybody good there? All right. So the second one, we have aluminum plus bromine. So once again, we have 2 elements. So anytime we have just 2 elements single by themselves, that means that we're going to have a synthesis reaction. So another synthesis reaction. And this time we have aluminum coming together with bromine. So when we do our crisscross, we take our charges and re-crisscross to get our product. Aluminum is +3, bromine is -1. So when we do our crisscross, we get Al1 and then Br3. So is this a balanced chemical equation that we have here? No. Okay. So what do we need to do to fix it? Okay. Perfect. So bromine, we have an odd number of bromines. So we got to make that even by putting a coefficient of 2 on the product side. So now we have 6 bromines and 2 aluminums on our product side. So what do I need to put in front of aluminum to fix that? 2 in front of aluminum. And what do we put in front of bromine? A 3. Perfect. So now we have a good balanced equation here. All right. Does that help a little bit with synthesis reactions? Good on those? All right, let's try these replacement reactions down here. So this has a different looking activity series than the one I gave you. It doesn't really matter how it's written, but like this one actually looks pretty nice. It's easy to read. So the most reactive things at the top and then the least reactive things at the bottom. And then it shows it separate for metals that are cations or positively charged ions and for anions. As remember, if it's a cation, it can only replace a cation, and an anion can only replace an anion. In terms of knowing whether or not a reaction will occur, single and double replacement is the trickiest because you have to know to look at the activity series for single replacement, and then you have to look at your solubility rules for double replacement. For synthesis, decomposition, and combustion reactions, you can always assume that those reactions occur. So, like up here, we didn't need to worry about whether or not they occurred. They're going to occur because they're synthesis reactions. Down here, we're going to have to think about whether or not the reaction occurs. So, let's start by just predicting the products as if the reaction were going to occur. So, copper here wants to try and replace something in iron 3 chloride. So what is copper going to replace? what is copper going to replace? Is it going to replace the iron? Yeah, it's going to replace the iron. Because copper is a cation, so it can only replace another cation. And really, this problem should tell you what oxidation state copper is in. Because remember, copper can have more than one charge. So really, it should tell you what oxidation state it's in. We're going to say that it's copper 3. So when we do our crisscross, we'll use the +3 charge. So copper, if it does replace iron, if it successfully replaces iron, we're going to kick iron out by itself. And then we're going to have copper crossed with chlorine. Copper is going to bond with chlorine. So we got to redo our crisscross. Copper with a +3 charge, and chlorine with a -1 charge. So when we crisscross, we get Cu1, Cl3. Okay. So now we need to make sure our equation is balanced. So we have copper, 1 copper, 1 copper, 1 iron, 1 iron, 3 chlorines, 3 chlorines. So we're already balanced, so we can just fill in a bunch of 1s. And now we just need to figure out if this reaction will actually happen. So for the reaction to happen, the thing that's by itself has to be more reactive than the thing that is getting kicked out. Because otherwise, copper, if it's less reactive, it's not going to be able to kick out iron. So you can think about it as like a big, strong, like your big, strong boyfriend or girlfriend. They're not going to let some weaker person come and kick them out of the relationship. And so atoms are just like that. If copper's not strong enough or reactive enough to kick out iron, then nothing's going to happen. You can put as much copper as you want with iron 3 chloride and nothing is going to happen. So we have to come over here and make sure that copper is more reactive than iron. So I see copper down here, and we need copper to be above iron, more reactive. I don't see iron down there, and look up here, and iron's actually way more reactive than copper. So this reaction is not going to happen, because iron is more reactive, it's stronger, it's more reactive than copper, so this is going to be no reaction, no RXN. RXN is just an abbreviation for reaction. Questions on that? Everybody okay with that? Somebody has a cute cat. Okay, so let's look at the second one. We have aluminum and we have hydrobromic acid. So aluminum, is that a cation or an anion? Aluminum is a cation. So it's going to try and replace the cation in hydrobromic acid, which hydrogen is the cation, it's the positively charged ion. So aluminum's going to try and replace hydrogen. So if it's successful, hydrogen's going to be kicked out by itself. And can I have hydrogen just like this, just H by itself? Can I write that?
No.
Why not?
Because it needs to have a two. It cannot exist on its own.
Perfect. Yes, it is a diatomic, so it has to come in a pair. It can never truly be alone. So hydrogen's kicked out by itself, but it's going to be H2 when it's by itself. Okay? And then our other product is going to be aluminum, which we know is a +3 charge bonded with the bromine, which has a -1 charge. So when we do our crisscross, we get Al1Br3. Okay? So now we need to balance this equation. What is out of balance here? Hydrogen. Everybody knows hydrogen. Okay, so how can I fix the hydrogen?
Add a 2 in front of the second reactant.
Okay, so I can put a 2 here. Okay. What else is out of balance? Bromine. Okay, so now I have 2 bromines here and 3 over here. What's the problem with that?
Bromine has an odd number.
Okay, so what do we need to do to fix that?
A coefficient of 2.
In front of which one?
The product.
In front of the product. So in front of aluminum bromide, I'm going to put a coefficient of 2 to make my number of bromines even. So now I have 6 bromines. So what do I need to fix over here? Okay, so I have 2 aluminums. So what can I put in front of aluminum on the reactant side? I can put a 2. Okay. And what else is wrong? Is it balanced? Now bromine's wrong. Okay, so I need to kind of reassess this number here. So what do I need my coefficient to be in front of HBr? I need it to be 6. Okay, so instead of having this 2 here, I'm going to get rid of that. I'm going to change it to 6. Okay, and now, so I fixed bromine, but what about hydrogen? So I now have 6 hydrogen, so I need to put a 3 in front of my H2 on the product side. So this was kind of a challenging one. This involved a lot of guess and check, and that's kind of what balancing is. Usually you can get it in a few guesses, but sometimes we have to kind of go back and be like, yeah, that coefficient didn't work, I'm going to change it to fix something else. So you have to be willing to guess and check a little bit and just work with the coefficients until you get it balanced. Okay, so let's look and figure out if this reaction will actually happen. So aluminum, for this reaction to happen, aluminum has to be more reactive than hydrogen. It has to be higher in our activity series than hydrogen. So hydrogen's right here. And I need aluminum to be higher. Okay, and aluminum is way up here, so it is more reactive. It will be able to kick hydrogen out, so there will be a reaction. So I'm going to put Rx in. There will be a reaction here. Questions on any of that? Okay, so the next one we have hydrogen reacting with aluminum oxide. So hydrogen's a cation, so it's going to try and kick out the cation, aluminum. And if it succeeds, aluminum's going to be kicked out by itself. I'm going to switch colors again so it's easier to tell the work apart for the different problems, okay? So if it succeeds, aluminum's going to be kicked out by itself. Can aluminum be by itself like this?
No.
Can it be? Is it a diatomic?
I don't think so.
Is it a diatomic? Remember, H2 into O2, F2, Cl2, Br2, and I2. Now let me real quick show you that on the periodic table. Okay, so there are 7 diatomics, and they make a 7 on the periodic table. So from nitrogen over to fluorine, and then down to iodine, it makes a 7 on the periodic table. But if you count up, 1, 2, 3, 4, 5, it's only 6 elements. The 7th one, don't forget, is hydrogen, and he's over here by himself. So it makes it maybe a little easier to memorize to know that they all make this L shape. They make a 7 on the periodic table, and there are 7 of them. H2, which is way over, into O2, F2, Cl2, Br2, and I2. Those are the diatomic elements. Whoops, dropped my folder. Okay, so let's see. So aluminum is not a diatomic, so it can stand alone by itself. It was kind of a trick question, so sorry about that. So aluminum is going to be kicked out, and then we're going to have hydrogen and oxygen together. So we need to recross. We're going to have H plus and O2 minus. So when we do our crisscross, we're going to get H2 and then O. We're just going to get water. H2O. Okay. So now we need to balance our equation. What is out of balance here? Cool, yeah, amount of oxygen. So we have 3 on the reactant side and only 1 on the product side, so how can we fix that? Perfect. Yeah, 3 in front of H2O. Okay, what else is out of balance?
The amount of aluminum.
Okay, how can we fix that? We have 2 on the reactants and only 1 over here on the products. Yep, put a 2 in front of aluminum. Anything else?
When we put the 3 as the coefficient of H2O, we knocked hydrogen out of balance.
Yeah, we did. We knocked hydrogen out of balance. We have 6 hydrogens now, so what do we need to put over here? A 3. Perfect. Okay, and then everything look good to you guys? Looks pretty good to me. We have 6 hydrogens, 2 aluminums, 2 aluminums, 3 oxygen, 3 oxygen. So I'm going to fill in my 1 here. And now we need to decide if this reaction will happen. So we need for hydrogen to be more reactive than aluminum. Hydrogen needs to be higher in our activity series than aluminum. So let's find one of those things. Let's see. Hydrogen's here. This is not boding well. Aluminum's all the way up here. So hydrogen is way less reactive than aluminum. So this reaction is not going to happen. It's going to be no reaction. Okay. So do we want to keep doing more single replacement, or do we want to switch over to double replacement?
Double.
All right. Cool. Let's do some double replacement. Let's see. Find my example problems for that.
And can we also go over the letters in parentheses that go after the?
Yes. Yes.
I don't understand those at all.
Okay. So that's actually most important when we're talking about double replacement reactions. Because double replacement reactions, for them to happen, all of the things that make them happen or not happen have to do with the state of matter that we start with and we end with. So remember, for a double replacement reaction to happen, we need 2 reactants that are what? You can look back at your notes if you need to.
They have to be cations.
Not quite. What state of matter do they have to be? Remember, they have to be aqueous.
I didn't see that in the minute.
It's
Was saying that on the section with replacement, then when you went to double replacement, it said cations is 2 ionic compounds switch and pair with the other anion.
well, that's true. That's what's
I must have just missed it.
So that's what's happening in a double replacement reaction. The cations of each compound are swapping places. But for the reaction to happen, like for it to actually occur, so like back with single replacement, remember, we were looking at whether or not the lone element is more reactive than the one that it's replacing. So that was the requirement for a single replacement reaction to occur. But for a double replacement reaction, we have to have 2 reactants that are aqueous. So in this first problem, it actually gives us the state symbols. It tells us that both of them are aqueous. But if it didn't give it to you, you need to look at your solubility rules and determine if they are aqueous to make sure the reaction occurs. Aqueous just means that they're dissolved in water. They're in solution, so they're dissolved. And there are a couple of things that are always aqueous, or you can assume are aqueous. So acids, so anything that starts with hydrogen, and bases. So if it's something and then OH, then the hydroxide ion, then those are pretty safe to assume that they are going to be dissolved. So sometimes like if your solubility rules don't say that the hydroxide would dissolve, if it's reacting with an acid, it's going to dissolve because it's going to react because of the acid that is there. And we haven't learned about acid-base reactions yet, so you don't need to like fully understand why that is. Just know that if you see an acid or you see a base, which I don't see any here, but like a base would be like calcium hydroxide, CaOH2, or sodium hydroxide, NaOH. Anything hydroxide, those are bases, and so when we have an acid reacting with a base, the reaction will happen. So this is the requirement for the reactants. We need 2 reactants that are aqueous. Then for the products, we need one product that is either what or what? Anybody remember? We need one product that's either, I'll give you a hint, is either a solid or is what?
Water.
Or is water. Perfect. Exactly. So an acid-base reaction will produce water, and those reactions, like I said, those will occur because the acid will dissolve the base if it's not already dissolved, and they'll react together to make water and then a salt that's usually going to dissolve. So that's one type, is a neutralization reaction. And then the other type of double replacement reaction is a precipitation reaction, which is one that produces a solid. And so these do take a lot of practice to get the hang of predicting whether or not the reaction will occur. Predicting the products is not super difficult. Like, it's not really that much more difficult than single replacement. But knowing whether or not they occur and being able to kind of go through this list of requirements, that does take a lot of practice. So that's why I have the whole video that goes with the worksheet where I'm walking through each problem, because it does take some, just like doing it over and over again to remember what the requirements are. So like for this first reaction, let's look at this one. So we have copper nitrate reacting with, copper 2 nitrate reacting with iron 3 chloride. So our cations are going to switch. So copper is going to come and pair with chlorine, and iron is going to pair with the nitrate. And it's important to note that on the other side, our cations or metals are going to keep their same oxidation state. They're going to keep the same charge. So copper here, nitrate, each nitrate has a -1 charge, and we have 2 of them, so it's a total of -2. So we need +2 to balance it out. So copper is going to have a +2 charge on the reactants, and it keeps that +2 charge on the product side. Does that make sense? So when we re-crisscross and we do copper crossing with chlorine, copper is going to keep this +2 charge, because otherwise you don't know what the charge would be. And chlorine's going to always has a -1 charge, so we're going to re-crisscross on the product side. So anyway, I'm going to pause for a second. Anybody have questions on that? Okay. Stop me if you do, okay? Okay, so copper and chlorine. So copper, we get 1 of those, and then we're going to end up with 2 chlorines. Okay, and I'm going to put parentheses to put my state symbol in, because I know I'm going to need to determine what the state would be, so I know whether or not the reaction will happen. And then my other product is going to be iron with nitrate, Fe. So we have chlorine, we have 3 of them, each with a -1 charge. We have -3, so we need this to be +3. So +3 on iron, and then it's bonding with nitrate, NO3. Nitrate has a -1 charge, so we're going to get Fe1, and then we're going to end up with 3 NO3. So I'm going to open parentheses, put NO3 in parentheses, close parentheses, and then bring down this 3 outside the parentheses. And then I'll put parentheses for my state symbol. Okay, so this is a lot. This is a lot of work. I'm going to be real honest here. It's just a lot of work, a lot of steps. So we've now predicted our products. We've redone our crisscross to get our products. And now the next step here, I like to balance next, so I don't forget to balance my equation. You could put the state symbols in next, but I always like to balance right after I predict my product, so that way I don't forget about balancing. So what's one thing that's out of balance here? There's a whole lot of things, but so we have 2 nitrates on the reactant side, we have 3 on the product side, we have 3 chlorines on the reactant side, and only 2 on the product side. So we got a whole bunch of stuff to fix here. What's one thing that we could do to start fixing this?
Wait, can you say that again? I'm sorry, I just
Yeah,
so much.
you are good. So I'm moving a little closer because I know these subscripts are a little bit dull. So we have 2 nitrates on reactant side, and we have 3 over on the product side. And then we have 3 chlorines on our reactant side, and we only have 2 chlorines on the product side. So what's something we could do to start fixing this? Yep, Fe's iron. So if we put a 3 here, the iron chloride. Well, if we So if we put a 3 here, we're going to end up with 9 chlorines. Is there anything we multiply? 2. Perfect. Okay. So we have 2 so we have 6 chlorines. I love that. Okay. And so you're saying we should put a 2 in front of the copper chloride? Or not a 2, you said a 3? Okay, 3 in front of copper chloride, because that fixes the chlorines. Now we have 6 chlorines on each side. Okay, good. That sounds good. What else do we need to do?
We need to fix the amount of copper now.
Yeah, so we have 3 coppers on the product side. And we fixed this over here, so what do we put in front of copper nitrate?
We need to put a 3 there.
Okay. Okay, so now we have 6 nitrates, and we only have 3 over here, so how can we fix that?
We need to put a 2 in front of the iron nitrate.
Beautiful. Okay, so now let's go back and check. Because we have a coefficient in front of everything, but we should make sure it's actually balanced. So we have 3 coppers on the reactants, 3 coppers on the products, 6 nitrates on the reactants, and 6 nitrates on the products, 2 irons in the reactants, 2 irons in the products, and 6 chlorines in the reactants, and 6 chlorines in the products. Okay, so we are good and balanced. Okay, so we predicted our products, we have our balanced chemical equation. Now we need to put in our state symbols so we can tell if the reaction will occur. So let's find our solubility rules real quick. Wonder where I put mine. Little piece of paper. Well, here. I have them on my folder so we can look at them. Okay, so copper chloride. Let's see. So you do get to use this as a reference sheet on your quiz and test. When you go to college chemistry, they're going to probably make you memorize this, but there's already so much in 10th grade to memorize that I just don't think it's worth your time to worry about memorizing this right now. But you might have to eventually, but just not right now. So all you have to be able to do is use this sheet. So I have copper chloride. So I need to look down the sheet and figure out where it says something about either copper or chlorine. So what's the first rule that talks about either copper or chlorine? Like rule 1, rule 2, rule 3, rule 4.
Rule 3, the compounds, it talks about chlorine.
Perfect. Okay, so it says compounds of chlorine, Cl-, Br-, and I-. They do generally dissolve. So they are soluble, but there's a few exceptions to that rule. So compounds of chlorine generally dissolve unless the chlorine's bonded to silver, mercury, or lead. So we need to look down here. We have chlorine bonded to copper, which is not an exception, so this is going to dissolve. So that means that our state of matter is going to be aqueous, dissolved in water. Does that make sense?
Yes, ma'am.
All right, cool. Because this is kind of complicated, so if you get confused, please stop me and let me know. All right. Okay, so then we have iron 3 nitrate. Okay, so what's the first rule that talks about iron or nitrate?
The second rule talks
Yeah.
about nitrate.
Perfect. So the second rule talks about nitrate, and it says all compounds of NO3 and C2H3O2 generally dissolve, and there are no exceptions to that rule. So every single compound that contains NO3 will dissolve. So this is also going to be aqueous. Okay. So now that we have all our state symbols filled in, is this reaction going to happen?
Yes.
So do we meet the first requirement that both reactants are aqueous? Do we meet that requirement?
Yes.
Yes. Okay. Do we meet the requirement that one product is either a solid or water? Do we have a solid or do we have water?
Yeah.
Okay, so aqueous does not mean that a product is water. Aqueous means that something's dissolved in water. We have to have a product that is H2O. Does that make sense? I think that might be the point of confusion there. So here we have an aqueous solution of copper chloride, meaning that copper chloride is dissolved in water, but our product, we don't have a product that is H2O. So it doesn't meet the requirement of water. Do we have a solid? No, we don't have a solid either, because both of these things are dissolved. So we don't have a solid and we don't have water. So we do meet the reactant requirements, but do we meet the product requirements? No, we don't meet the product requirements, because we would need one of these things to be a solid, to have an S in parentheses, or we need one of them to say H2O. Does that make sense? It's kind of confusing. Like, this is confusing. It's probably the hardest part of predicting products. So this would be no reaction, because we don't have a solid and we don't have a product that is water. Do we want to do another one? All right. We'll probably have time for one more. Let's see. Hang on. Let me think about it real quick and find one that'll be different. Okay. All right, next one will be good. Okay, so we have two aqueous reactants. We don't need to worry about state symbols there. So our double replacement, if it happens, barium's going to bond to sulfate, and the ammonium ion is going to bond with the acetate ion. Okay, so we need to redo our crisscross. So we're going to have barium bonding with SO4. Barium's going to have a +2 charge, and SO4 has a -2 charge. So when we do our crisscross, we get Ba2SO4 with a 2, but then those 2's cancel out. So just BaSO4. Everybody with me so far?
Yes, ma'am.
All right, just make sure. Okay, and then we have NH4, which ammonium has a +1 charge, and it's going to be crisscrossed with acetate, C2H3O2. The whole thing has a -1 charge. So when we crisscross, we get 1 NH4, and we get 1 C2H3O2. So since there's only one H, we don't need any parentheses there. And then I'm going to put my parentheses for my state symbol, because I know I'm going to have to fill those in. Okay? Okay, so what's the next step?
Find whether or not it's a balanced equation.
Perfect, so we're going to balance. Okay, so we have barium, one over here, one over there. That looks good. We have 2 acetates on the reactant side. Oh, we only have 1 on the product side, so what do we need to do to fix that?
We need to put a 2 in front of the product that is
Ammonium acetate. Yeah.
ammonium.
Okay, so we'll put 2 there. Yeah, it's a complicated name. Thought I'd help you out. Okay, so now we have 2 ammoniums, and we have 2 ammoniums on the reactant side, so that matches up nicely. And we have 1 SO4 and 1 SO4. Okay, so I think we're balanced. Did anybody see anything that looks wrong?
No, not at all.
Alright, so I'm going to fill in some 1s. Okay, and now what do I need to do?
We need to determine if they're aqueous or not.
Yeah, we need to determine whether the reaction occurs. So either of these are going to be aqueous or they're going to be a solid. If it doesn't dissolve, it's just going to sit as a solid at the bottom of our beaker, our test tube, or whatever we're doing our reaction in. Okay, so let's see. Running out of room here. Let's see. So we have, maybe if I put it over here. We have barium sulfate, BaSO4. So we're looking for a rule that either includes Ba or SO4. What rule is the first rule to include one of those things? Yeah, okay, so it says compounds of SO4 generally dissolve, but there are some exceptions, and barium is an exception to that rule. So barium bonded to SO4, that's not going to dissolve. So what state symbol should I put next to BaSO4?
Solid.
Yeah, so this is our solid, okay? And what about ammonium acetate? So where's the first rule that you see either ammonium or acetate? Oh yeah, I didn't even notice the ammonium down here. Yep, and I was also looking at the second rule with C2H3O2. And both those rules say that compounds of NH4 dissolve in water, there are no exceptions to that, and compounds of acetate dissolve in water, no exception to that either. So that one definitely will dissolve. So what symbol are we going to put next to ammonium acetate? AQ. Okay, so let's go through and see if it meets the requirements for the reaction to occur. So, do we have two reactants that are aqueous?
Two reactants are aqueous,
Yes, okay, so we meet the reactant requirement. Do we have a product that is either a solid or water?
Yes.
Yes, so we have a solid here. We have barium sulfate, which is a solid, so that's what we call a precipitation reaction, which when you get to zone 3 on your matrix, you'll actually do a mini lab where you get to see a precipitation reaction and what that looks like. Because it doesn't look like a giant chunk of something, it's like just powder basically, but it is a solid that's not dissolving. So this reaction will happen because we meet both those requirements, so I'm going to put reaction here, or XN, not that you could see it because I was too far away. Okay, well we're about out of time, but I can leave these up if you want some extra problems to practice. You can take a picture or look at the YouTube video later. And the other ones are combustion, and then, well, these are acid-base ones at the bottom, so those are also double replacement. Let's do one combustion one real quick, just so we can make sure that we're on the same page there. We haven't talked about that. So combustion reactions are really easy to predict the products because they always have the same two products. So anytime you have a hydrocarbon plus O2 gas, it's going to be a combustion reaction. So it doesn't actually show the O2 here, but it does show that it's a hydrocarbon, and it tells you that they're combustion reactions. So hydrocarbon and then O2 gas, what are the two products of a combustion reaction?
Carbon dioxide.
Perfect.
And water.
CO2, yep, and H2O. Okay, so that's always the same thing. So like we can fill all these in. So C3H8 plus O2 gives us CO2 and H2O. C2H5OH plus O2 will give us CO2 plus H2O. So they're super easy to predict the products. The tricky part about combustion is balancing, because they're usually the toughest ones to balance. So let's do a couple together. So what do you notice about oxygen in these problems?
There's normally 3 oxygen.
Yeah, so it's in 3 places, like at least 3 places, and number 25 is actually in all 4 compounds. So what we want to do with that is we want to leave it till the end to balance. So we want to focus on carbon and hydrogen first, and then we'll come back to oxygen at the end. So I see there's 2 carbons on the reactant side, so I need to put a 2 in front of CO2 on the product side. And I notice there are 2 hydrogens on the reactant side and 2 on the product side, so that looks good. So now I'm going to come back to oxygen. I say, okay, so there's 4 oxygens over here, and there's 1 over here, which gives me a total of 5. What's the problem with this?
It's an odd number.
Yes, perfect. It's an odd number. So here's the trick to combustion reactions. If you get into a scenario where you have an odd number of oxygens, go ahead and put a decimal, and then you're going to double all your coefficients, and that'll get you back to whole numbers. So what decimal can we put in front of O2 so we have 2 times some number that equals 5? In other words, what's 5 divided by 2?
2.5.
Yes. Okay, so I'm going to put 2.5 here, and I know that I can't have a decimal in the end. Okay, so I'm gonna fill in my ones. So C2H2, we didn't put a coefficient, so that's a 1. We didn't put a coefficient here, so it's a 1. Okay, but now I need to make this a whole number. So I'm gonna go through and I'm gonna double all my coefficients. It's basically like algebra. What you do to one side, you can do to another. What you do to one coefficient, you can do to all the rest. So double this and make it a 2. I'm gonna double this and make it a 5. Double this and make it a 4. And double this and make it a 2. And then I have a balanced equation with all whole numbers. Does that make sense?
Somewhat.
Okay.
But there's like a short method to do.
Yeah, okay. So let's do the second one. Let's look at the second one. So 3 carbons on the reactant side, so I need to put a 3 in front of the CO2 on the product side. And I have 8 hydrogens on the reactant side, so I need to put a 4. 4 times 2 gives me 8 hydrogens on the product side. So now, let's do oxygen last. We have 2 times 3, we have 6 oxygens here. And then we have 4 oxygens here. So this one actually came out to a nice even number. So I just need to put a 5, so I have 10 oxygens on the reactant side. So that one was easy. We didn't have to use our doubling method. Let's look at number 25. So here we have 2 carbons. So I need to fix that by putting a 2 in front of CO2. I have 5 hydrogens plus 1 hydrogen, so I have 6 hydrogens here. So I need to fix that by putting a 3 in front of H2O. Okay, now I need to fix oxygen. So I have 2 times 2, 4 oxygens. And then I have 3 oxygens. That gives me a total of 7. And over here, oh, this one's tricky because we have an oxygen right here and the oxygen here. So I have 1. So I need to have 6 more here. So what do I need to put in front of O2 to make a total of 6 oxygens here?
A 3.
Yeah, 3. So that one actually worked out nicely as well. I'm looking for one that will work out like the first one. So let's do the last one as well. Let's see. I'm going to switch colors. That'll be our last problem of the night. Let's see. CH4 plus O2 gives us CO2 plus H2O. So combustion reaction. So we have 1 carbon here, 1 there. We have 4 hydrogens and 4 hydrogens, so I need, or 2 hydrogens, I need to double this. So now I have 2 oxygens and 2 oxygens, so it gives me 4. Oh, this is also easy. 2O2. Alright, well none of the other ones were hard, like the first one. But if you need more practice balancing combustion reactions, I do have practice sheets that have example problems of combustion reactions on them. But when you get in that case where you have an odd number of oxygens, put that decimal number in and then just double all your coefficients to get back to a whole number. So, any other lingering questions before we break for the night?
So do you only use the doubling method when there's a decimal?
Yes, only when you've had to put in a decimal, because you want the lowest possible whole number coefficients. But like 2, 5, 4, and 2, there's nothing we can divide all those by. So those are the least common numbers, basically. If we had 2, 4, 4, and 2, then we could divide everything by 2. So that wouldn't be reduced, basically. But here we can't divide them all by the same thing. Does that make sense?
Yeah.
Okay.
Yeah.
All right. Anything else?